Hello everyone, I'm Captain Jeremiah Bill,
I'm Lieutenant Michelle McGee.
and we are both students here at the Air Force Institute of Technology, and today we're going to talk through uncertainty analysis through design threads. So today we will be discussing the Bayesian Enterprise Analysis Model, or BEAM for short. BEAM is a high-level combat modeling tool that allows analysts to quickly evaluate both military strategies and force compositions. BEAM contains several unique features. First, BEAM is a very aggregate model with a lower resolution than traditional combat modeling tools. This allows for rapid scenario development and evaluation that is generally not possible with some of the more fine-grained combat modeling tools. Additionally, BEAM models uncertainty using discretized probability distributions in a thread-based process. BEAM's final output is a probability distribution as opposed to a single point estimate. Finally, the prototype BEAM application is very flexible and can accept mission success probabilities from a variety of different sources. Here's today's agenda. First, I will walk through the thread-based probability distribution process that we employ in BEAM, showing some experimental results that validate the process. Then my colleague, Lieutenant McGee, will cover the BEAM application itself and describe some current uses of the tool here at AFIT. So when modeling uncertainty, there are generally 4 different approaches that you can take, and each has its own set of pros and cons. The most powerful approach is to use analytic results such as statistics or Markov chains, but this process is generally limited to very specific applications for which we have analytic results. Another powerful option is to use Bayesian networks for modeling uncertainty. These are much more flexible than straight analytic results, but they are computationally expensive. The posterior distributions in a Bayesian network are a very expensive process to compute and usually involve some sort of approximate inferencing or map approximation. On the other hand, you can use some sort of discretized probability distribution approach. This is what we refer to as our thread-based approach, and I'll cover the process in detail in the next few slides. We note here that it is much faster than using a full Bayesian network, but you do lose some information by employing a discrete probability distribution. It has applications to a fixed state space over time. And finally, one of the most popular tools for modeling uncertainty is through Monte Carlo processes. Discrete event and time simulations are both examples of Monte Carlo techniques, and they are employed heavily at Headquarters Air Force and in other units within the DoD. They provide a very flexible approach, but the results are generally given as point estimates and often require expensive replications of complex scenarios in order to provide stable results. So here's an outline of the algorithm that we use for our what we call our thread-based approach. First, we define probability distributions for each simulation state. Then, each distribution is discretized into some number of equal probability bins. Using equal probability bins instead of equal step size bins has the benefit of reducing some of the computational resources that you would use churning through calculations on the small amounts of probability mass in the tails of a distribution. So that's kind of done away with by using equal probability bins. And for any 2 distributions, you can perform any arithmetic operation such as multiplication or addition by taking the midpoint value of each bin and performing all the pairwise combinations of either addition or multiplication between the bins. So Lieutenant McGee has an illustration of this process later on in the discussion of the BEAM application itself. But for just a brief example, if we have 2 distributions that we discretize into 4 bins, and we would like to add them together to perform a convolution, we take the midpoints of each bin in each distribution and take all the pairwise combinations and add them together for a vector that's length 16. Then we take this vector and order it from least to greatest and re-bin it by taking the average of the first 4 bins, the second 4 bins, and so on. This process repeats through each step of the simulation and results in a total distribution of assets in a simulation through time. In order to establish the validity of this process, we ran several experimental scenarios using known analytic results. In this case, I chose to evaluate the amount of information retained through our discrete thread-based process in terms of computing the convolution of a number of different random variables. So using results from statistics, we have closed form solutions for the convolutions of IID normal random variables, non-IID normal random variables, exponential and gamma random variables, among several others. So we could measure the error of the beam process as opposed to, say, a simple Monte Carlo simulation process in terms of the exact error based on the analytic solution. So in each convolution, we directly compare our beam mean and variance error estimations to the error of a similar Monte Carlo process. Here are the results from the IID normal random variable case. In this case, I instantiated 30 random variables, all IID normals, and performed a convolution using the discrete beam process that I described earlier, and a simple Monte Carlo process. The computational resources required to perform the beam addition process grows as the number of discrete bins grows, similar to how the resource demand grows for a Monte Carlo process with the number of replications performed. With that in mind, we did a head-to-head comparison between the error of the beam process at n bins versus the error of a Monte Carlo process at n replications. One thing I want to point out here is that the y-axis on both of these graphs are of different scales, so keep that in mind as you're kind of processing these. What we found is that for symmetric distributions, our discretization process perfectly captures the mean regardless of the number of bins used. This provides a substantial benefit over Monte Carlo estimates. There's no free lunch with this, however, and you do lose information in terms of the variance of the final distribution. But you can note that the variance error rapidly and smoothly approaches zero as the number of bins increases. And here are results for the non-IID normal case. Again, we instantiated 30 random variables, this time with a range of different mu and sigma values. And then we performed both the Monte Carlo addition process as well as the beam process. And the results are nearly identical. You see that we don't lose information in terms of the estimated mean of the final convolution, but you do lose out in terms of variance. But again, it rapidly and smoothly approaches zero. And here are the results for the gamma random variables. You can see that the Monte Carlo mean estimation struggles at the beginning and has a very much more jagged approach. Also here with gamma random variables, since it's not a symmetric distribution, in terms of the mean estimate, you also have some error there with small numbers of bins that again kind of rapidly approaches zero error as your number of bins grow. And similarly for exponential random variables. In summary, our process outperformed Monte Carlo techniques in the estimate of convolution of random variables in all cases. The number of bins used for our process is analogous to the number of replications required for a Monte Carlo process. However, the resulting output that we get is a full distribution. And in each instance, there's kind of a knee in the error curve for the beam process at around 20 bins, which suggests that this might be a good rough estimate for the resolution needed to get good results with our process. Some future work includes expanding this to more general convolutions, as well as using product distributions to measure how the multiplication process works. Now I'll turn things over to Lieutenant McGee, who will go through the beam application in more detail and describe how it is currently being used.
Great, thank you. Department of Defense analysts use a hierarchy of conflict models which consist of levels varying by resolution and scope. Resolution indicates the extent of detail represented, whereas scope assesses the extent of domains and of functions modeled. A more aggregate model naturally has less resolution and a broader scope. Traditionally, military campaign models have been considered the most aggregate type of military model. There, entities that represent individual tanks, planes, and ships are simulated. Currently, the most common campaign models allow for varying force structure combinations. However, they present a myriad of difficulties in modifying the higher level strategy. Because of such shortcomings, the analysis organization at Headquarters Air Force initiated development of a new modeling approach of combat. Beam fits in the defense enterprise level, which has a broader scope with less resolution than campaign models. Beam is constructed to evaluate decisions made at this level in order to investigate military strategies and force compositions across a variety of potential types of future wars. The main contribution of Beam is its ability to rapidly evaluate both alternative military strategies and force compositions in potential future wars. It can quickly evaluate different strategies for each of the warring opponents to test whether an adversary can adapt to counter an apparent strategic advantage. By definition, a model at the defense enterprise level is formulated with less resolution than campaign models. Whereas campaign models simulate model units, such as individual ships and aircraft, the Beam government development team chose to model the distribution of these entities grouped by asset type. The benefits include being able to rapidly generate joint campaign scenarios, which means that Beam is able to represent combat units and systems from all military services. Beam incorporates missions for ground units alongside ship, aircraft, and satellite missions to represent an overall combat effectiveness in the same construct in which the military services actually organize. Also, it can quickly evaluate the impact of military strategies, force structures, and infrastructures. By evaluating each scenario sufficiently quickly, the large decision space of potential strategies and force structures may be searched. Also, Beam accounts for friendly and adversary adaptation and quantifies outcome uncertainties. In terms of uses, Beam can examine a broader trade space, identify key drivers in both assets to defend and targets to attack, experiments with technologies, con-ops, strategies, etc. Moreover, Beam can be used to identify promising solution areas as well as provide filter for higher resolution models. Our approach is Bayesian in the sense that the number of each type of asset are treated as random variables. Since a distribution of dispersed assets cannot have a specific geographic location, we model those distributions within major geographic regions in the combat theater. Within Beam, these are represented as maritime, land, and rogue. We represent those distributions consistent with Bayesian applications by dividing the distribution into probability bins. A 2019 AFIT Master's student, Lieutenant Salazar, demonstrated the similarity of state distributions for the MM1Q. The Bayesian network distributions of states are generally within 1% of the distribution derived from replications of either a discrete event simulation or a time step simulation. Next, we will discuss how Beam actually works. There are two sides, red versus blue, and the simulation is given the forces positioned in the regions, the mission effectiveness stated in probabilities for the range of affecting assets, and the strategy stated in priorities of missions by combat phase. There are 3 combat phases in Beam. Each time step has 4 cases per side, which starts 16 threads. Each side in each thread for each time step completes a myriad of tasks, including predicting the adversary's forces and strategies, allocating assets to missions to achieve their own strategy, adjudicating combat with outcome distributions of assets affected, stopping threads that have achieved phase objectives or are lost, combining all the remaining asset outcomes to new asset distributions, updating cases and starting the new threads. And then each of these steps is repeated for each thread for each next time step. One Beam run calculates all the asset distributions, which means that the same inputs will yield the same results regardless of time. This is an explanation of what is occurring in the black box of Beam runs. Each type of mission changes the asset probabilities, so all involved offensive, defensive, and targeted assets are affected. A probabilistic range of outcomes is modeled rather than just a single probability of damage. For each asset, thread, region, and time step, all outcomes are combined involving that asset to the new asset distribution. The asset distributions are combined across threads, and then new cases are created and new threads are started in each time step. Here's one of the visual graphs of the beam output for a near-peer air-sea conflict. The beam results show probability of achieving combat phase objectives for each time step. As we move across the screen from left to right, from phase 1 to 3, we want to look at where the most rapid slope changes occur, because that difference is the most significant information in terms of what assets are significant to achieving that particular phase's objectives. Here's another evaluation of 2 military campaign strategies. The table shows the performance metrics between strategy A and strategy B in achieving the goals of effectiveness and the average number of days. The key metric is the percentage that the strategy achieved its goals. As we can see, although strategy B takes longer, it has a much higher probability of success than strategy A. This is a key benefit of BEAM because we can evaluate both strategies and the force compositions in one run. Here's a more detailed breakdown of the output that BEAM provides for a single scenario. BEAM stops threads that are deemed to have achieved their objectives or those that have been deemed lost. Probability distributions for each asset type in each region are calculated. The large deltas between winning and losing asset inventories indicate either critical friendly force drivers or adversary critical targets. This equates to the assets that we want to protect or the critical targets that we want to attack. This can be seen as the last column of the table, the winning and losing delta. The largest magnitude deltas indicate to focus on altering the force structure for that particular asset group. Lastly, BEAM allows the analyst to break this particular table down even further if more detailed information regarding the threads are desired. The AFIT OR Master's Course core work has moved to implement BEAM into the course cost and risk analysis. The project's scope is to apply a stochastic preemptive goal program approach to balance force effectiveness and costs. The costs are limited to R&D, production, and annual ONS. The essence of this project is to redesign the Air Force's force structure from a blank sheet of paper. We are determining what systems to redesign, produce, and in what quantities. We are taking this from the perspective of if the Air Force force structure was operating in a long enough time frame that we would desire to completely reshape and redesign the force structure. BEAM is then used to evaluate the effectiveness in 3 hypothetical scenarios of land, maritime, and rogue. The end result is a proposal of a new force structure. In summary, the thread approach is a novel way to model uncertainty. Simulated state distributions are represented in equal probability bins. The threads are started based on those probability bins, and the threads conduct dynamic calculations to represent the simulated system, including the range of uncertainty of outcomes. The resulting probabilities are combined into new simulation state probability distributions. Overall, the goal of BEAM is to evaluate a scenario sufficiently quickly so that the large decision space of potential strategies and force compositions may be searched. It is already a working model and continues to be improved upon in both readily available data and automated searches. This concludes our presentation. Thank you for attending. Are there any questions?